Hi, everyone. So we're going to do section 9.2 on arithmetic sequences and partial sums. Well, what is an arithmetic sequence? Here's an example. By the way, it's pronounced arithmetic, not arithmetic. It's arithmetic as an adjective. All right, what's the next term in the sequence? You can think of a recursive relationship here. The next number in the sequence will be 14, because what are you doing to each term to get the next term? You're adding 3. So if I tell you right now, hey, to get your sequence, begin with 2, and then keep adding 3, then you get a sense of the sequence, right? Then in principle, you can get any term down the line. So an arithmetic sequence is determined by its initial term. Here it's a sub 1, although again, in other sequences, you might start with a sub 0 or whatever. Okay. Here, a sub 1 is 2. And also something called the common difference. That's basically the number that you keep adding over and over again. Here, it was 3. You keep adding 3 over and over again to get each new term. That's kind of a recursive way of looking at it. You take the current term, add 3 to get the next term. It's called the common difference, denoted by D. Now you might be going, why are you calling it a difference? Well, because we frame it as the new term minus the old term, right? The new term, 5, minus the old term, 2, is 3. So that's why we call this the common difference. Okay, here D is 3. Okay, it's a sub 2 minus a sub 1, or a sub 3 minus a sub 2, and so forth. Okay, so how can you get the common difference? For example, if these were like ugly fractions or something, and it wasn't obvious what was being added over and over again, then computationally, how can you figure out the common difference? Well, you could take the second term minus the first term, or the third term minus the second term, or the fourth term minus the third term, and so forth. The 1000th term minus the 999th term. And by definition, an arithmetic sequence has a common difference. This minus this, this minus this, this minus this. It's a common difference. It's the same number, in this case, 3. If you don't have a common difference, it's not arithmetic. All right. Sometimes one of these is easier. Depends on the numbers. So the following information completely determines our sequence. If I have a sequence and you care, then if I tell you the sequence is arithmetic, the initial term is a sub 1, which is 2, the common difference is 3, then you should be able to figure out, in principle, any term in the sequence. Although it may take some time. But what if I ask you for the 1000th term? Do you really want to sit there at your desk and go, okay, 2 plus 3 plus 3 plus 3 plus 3 plus 3? And I don't think so. It's not worth it, even for a test grade. All right. So we're going to talk about that issue in just a moment. Again, I was mentioning the recursive definition, the idea that, okay, a sub 1 is usually given, not always, but a sub 1 is usually given. And to get the next term, you take the current term and add D, the common difference. Okay, where K is a positive integer. All right. The arithmetic sequence, 25, 20, 15, 10. This time you subtract 5, which means that the common difference is negative 5. So you can have an arithmetic sequence that's decreasing. That means that D, the common difference, is negative. For example, 20 minus 25 is negative 5. Okay, like I was saying before, what if I asked you to find the 1000th term in a sequence? You probably don't want to go 2 plus 3 plus 3 plus 3 plus 3. Okay, can we find a closed form formula, right? Not a non-recursive. I might phrase it this way on the test. A non-recursive closed form formula. Meaning that, for example, the 1000th term would not be defined in terms of the 999th term or the 998th term. It's going to be defined in terms of n. Okay. So here's the idea. Let's develop it step by step. Let's begin with a sub 1 and keep adding d until we get the general expression for a sub n. All right. The first term, a sub 1 equals a sub 1. A horse is a horse. All right. And then the second term, a sub 2, is the first term, a sub 1 plus d, the common difference. Before it was 3, right? 2 plus 3 is 5. To get the third term, well, it's true that you get the second term, but here's the idea. What's the third term? It's going to be the second term plus d. But what is the second term? It's the first term plus d. So if you substitute this in for this, you get a sub 1 plus d. That's what a sub 2 is, right? A sub 2 is a sub 1 plus d, all plus d. What's that? That's a sub 1 plus 2d. Likewise, a sub 4 is a sub 1 plus 3d. Now, this makes sense because the idea is that if you want to go from the first term to the fourth term, right? You want to go from the first term to the fourth term. How many times do you add the 3? Once, twice, 3 times. There was a song called 3 Times a Lady. Once, twice, 3 times a lady. All right. Another way to look at it. Let's say that you're climbing a ladder or a staircase. You're at the first floor of the ladder, all right? And then you want to get to the first floor of the ladder. I'm sorry, the first step on the ladder or the first step on the staircase, all right? And you want to get to the fourth step on the ladder or the fourth step on the staircase. Well, how many steps would you need to take if you're going step by step? 1, 2, 3. So to get from a sub 1 to a sub n, how many do you step? How many steps are there? Not n, but n minus 1. That's often an issue in computer science. Are we dealing with n or n minus 1? I did a professor who called it the Fencepost Problem, right? If you have 3 fence posts, then you're trapping 2 regions in between. In general, to get the nth term, a sub n, you take the first term, a sub 1, and add d, how many times? Not n times, n minus 1. And remember, repeated addition is multiplication, right? For example, a sub 1 plus d, that's a sub 1 plus 2d. In general, if you're adding d n minus 1 times, you get this product. We're thinking, again, of multiplication as repeated addition. And that is the general nth term of an arithmetic sequence with initial term a sub 1 and common difference d. It's given by a sub n equals a sub 1 plus the quantity n minus 1 times d. In more advanced problems, you might not be given a sub 1. You might be given other terms or clues. Then maybe you solve for a sub 1 at some point. Sometimes systems are involved. All right. Again, you take n minus 1 steps of size d in general to get from a sub 1 to a sub n. Here n is 4. You add d 3 times. Oh, and this is a discretization of a linear function. Okay, it's basically linear. This is linear in n. Remember, these are numbers. A sub 1 is a number, d is a number. This ends up being linear in n. Okay, so an arithmetic sequence will always correspond to dots on a straight line. Pretend that's a straight line. All right, example. Find the 100th term of the arithmetic sequence 2, 5, 8, 11, and so forth. That was the first sequence I showed you. Assume that 2 is the first term, meaning a sub 1. Right? Or I should say it starts with n equals 1. I should have said that, really. Well, I mean, if 2 is a sub 1, you're looking for a sub 100, right? Find a sub 100. 2 is a sub 1. Okay. So we can use our handy-dandy formula because, let's use our formula, right? So we want to know the 100th term. Okay. So we plug in n equals 100, right? Because we want the 100th term. N equals 100. we know from before the common difference is 3. I mean, it's it's pretty straightforward here. You're adding 3 as your common difference to get each new term. So a sub 1 is 2. That's the first term. D is 3. I care about the 100th term. So we have a sub 100, n equals 100, right? Now again, if you didn't know this formula and you have your calculator in your hand and you love calculators, you could sit forever with your calculator. What could you do? You put 2 in your calculator and you keep adding 3. How many times? How many times do you add 3 to get the 100th term? If 2 is the first term. You add 3, not 100 times, but 99. My computer science professor called this the off by 1 bug, an OBOB, where in computer science, you often have to think, okay, am I dealing with n or n minus 1? Because these issues come about. You get 299. And of course, we follow the usual order of operations. The multiplication precedes the addition. And of course, any scientific calculator more than a couple of bucks would tell you that. All right, 299. You get it by taking 2 and adding 3 99 times. I think this is faster. You'll get the same result. Now, here I discuss the formula for the partial nth sum of an arithmetic sequence. Remember what this is. I'm going to pull back 9.1 because remember what this is. All right. S sub n is this over here, right? S sub n is this thing over here. It's the sum of the first n terms, the cumulative sum of the first n terms of any general sequence or series. Okay, so in this case, if you know that you're dealing with an arithmetic sequence or an arithmetic series, then this is the formula for the sum of the first n terms, assuming you're starting with n equals 1. I will not require you to use this on homework or exams, but be aware that it's here. It makes sense. The sum of the first n terms, it's equal to the number of terms times the average of the first and last terms. That kind of makes sense. It's like n times the midpoint of the extreme terms. Yeah, the number of terms times the average of the first and last terms. And I have an example. Okay, the 100th term is 299, but if you add everything from 2 up through the 299, you get 15,050, and you can use the formula for that. Again, this won't be on your final. If I have time, I'll send you some cute videos on how the brilliant mathematician Carl Gauss figured this out. Add the first 100 positive integers. Gauss's teacher gave this to the class as busy work while the teacher did something else. But Gauss came up with a very clever way of doing it, and there are cute variations on that. And actually, bear in mind, this thing here, this is a finite arithmetic series, right? 1, 2, 3, and so forth. That's an arithmetic sequence. You can think of the positive integers as a positive sequence. And you're taking the 100th partial sum. Okay. Next up, geometric sequences, partial sums, and series. Try to guess what we do here for geometric. And these are actually much more important than arithmetic in calculus, and we'll see why.